So in the last lecture, we looked at the topic titled root finding techniques. We considered various techniques for finding roots of nonlinear equations. Okay, so today what we'll be doing is to apply that knowledge to a chemical engineering problem. So there is this question on the board that says, in a chemical reactor, a reversible reaction occurs between species A and B to form C and D, according to the equation on the screen. So for that particular reaction, the equilibrium constant is 10 at the temperature at which the reaction is taking place. The initial moles of A and B, which are the reactants, are 2 and 3 respectively. C and D are initially absent. Calculate the equilibrium concentration of all species. So let me just give you a brief explanation of what the problem is before we just apply MATLAB to root finding, that I believe we already laid the right foundation in the last class. So you have a reaction taking place. The reaction is taking place between A and B, which is the reactant. So the forward reaction is producing C and D. But that reaction is reversible, meaning that the product C and D are also reacting to form the reactant back, which is A and B. So we are now told that, okay, at the temperature that we are looking at, the equilibrium constant is 10. So we want to know that what is going to be the concentration of all of the species that are involved in this reaction by the time equilibrium is attained. What is equilibrium? Now, when a reaction progresses, let's say for example, like in this case, there were no products before, there were no C and D. But as the reaction begins to take place, the products are being formed. So at the time that we attain equilibrium, what happens is that the rate at which we have products is the rate at which the product is going back to the reactant. So nothing seems to change at that point that we have equilibrium. But before equilibrium is attained, products will be formed. Okay? Changes will be happening. But once you get to equilibrium, you won't notice any other change because the rate of the forward reaction will be equal to the rate of the backward reaction. So we want to know, at that time that we have reached that state, what is now the concentration of species A and B? What is the concentration of species C and D? That's what we want to know. So based on the question, we are given what the initial concentrations of the species are. Species A, species B, C and D. We know what they are. So now we want to determine what will now be the concentration when we have attained equilibrium. So that's the question. So normally, when you want to represent a reaction taking place, in this case, is a reversible reaction. That's why you have the reversible arrow. One arrow going forward, one arrow going backward. So we can represent that reaction with the equation that you see on the screen, where small a, small b, c, small c and d, they are the stoichiometric coefficient of the species involved. So we have species A, species B, species C, species D. So if we compare this typical equation that represents a reversible reaction to the reactions that we are given, the reaction we are given for the problem we want to solve. So we can say that small letter A in this case equals to 1, right? Small letter B equals to 1, small letter C equals to 1, small letter D equals to 1. So in this case, they all have the same stoichiometric coefficient. But you should know that it's not in all instances that they have the same stoichiometric coefficient. It will depend on the reaction that you are giving. Okay, so going back to this, if you want to solve the problem at hand, what you need to do is to apply the principle of material balance. Now, in reaction kinetics that I teach you, I said material balance applied to a reaction is about the stoichiometric coefficient, how each of the species that makes up the system is being conserved, right? So now, if we want to apply the material balance to this, what we need to know is that, okay, what did we start with? So we are told that initially we have how many moles of A? Let's go back to it. We have 2 moles of A, 3 moles of B, 0 moles of C and D. Okay, so if the reaction wants to take place, based on that stoichiometric coefficient, if X moles of A has reacted based on stoichiometry, we believe that it's going to react with X mole of B, because based on the stoichiometry that they gave to us, they have the same stoichiometric coefficient, right? And the product that will be formed, since it was X mole of A, X mole of B that reacted, based on that stoichiometry, we expect to get X mole of C, X mole of D. So that's about the application of material balance. So we know what we started with. So if we started with 2 moles of A, by the time the reaction has happened and X moles of A has reacted, what will be left when we are now at equilibrium will be what we started from minus what we have taken from each of the reactants, right? And what we have as the product is what we had before plus what has formed. So we know what we had before for the product, and we know what has been formed based on the stoichiometry, which is the application of material balance in this case. So now what we can have at best based on that is just an expression. For example, we can have maybe 2 minus X as the concentration at equilibrium for A. Then we have 3 minus X for the concentration of B at equilibrium. And for C and D, we are going to have 0 plus X, right? 0 plus X. So that X is part of what we want to know. Then the value of 2 minus X, that's what we are asked to determine, and the value of 3 minus X. So that means that information is not sufficient. The material balance equation is not sufficient. So that is when we have to bring in another equation that can help us find what the value of X is, so that we can be able to get the equilibrium concentration as we are asked to determine. So the equilibrium constant expression is that second equation on the screen. So the expression says that the equilibrium constant, represented by K subscript EQ, is equal to the concentration of the product, each of the products, raised to the power of its coefficient, the product of it. So let's say we have species C and D in this instance, and like we have shown on this screen, their stoichiometric coefficient is C and D. So we raise the concentration to the power of their stoichiometric coefficient and multiply them together, then divided by the concentration of the reacting species raised to the power of their stoichiometric coefficient. You also multiply them together, all of the reacting species. So that will give you an expression. So if you combine that expression with the material balance expression I just explained to you, then you'll be able to solve the problem, which says that you should find what the concentration is going to be at equilibrium. So based on that explanation, we have the equation that was given to us, A plus B going to C plus D, and C plus D going back to A plus B. So we started with 2 moles of A, 3 moles of B, 0 moles of C, 0 moles of D. So since the stoichiometric coefficient is the same, so we said if X mole of A is reacting, so we are using negative because that means the reactant is going to be depleting. So that means minus X is leaving. Then it's the same amount of B that is going to deplete. And that same amount is going to be C and D that will be produced. But if the stoichiometric coefficient is not 1, 1, 1, then the factor is going to apply. For example, if we have A moles of A now, so what we can do, we can say minus AX, right, for A that is depleting. For B that is depleting is going to be minus BX. For C that is going to be formed is going to be CX. And for D that is going to be formed is going to be DX. So the stoichiometric coefficient is going to play a role. Okay? But here it's 1, so that's why it looks like everything is the same, because you have used 1 to multiply through. Then we said, okay, now the changes have happened. What do we now have in the system at equilibrium? So at equilibrium is going to be 2 minus X, X that has gone. And B is going to be 3 minus X, X that has gone into the reaction. And for C is going to be X, because we started with 0, 0 plus X will give you X, and for D is going to give you that. So that is the equilibrium concentration to an extent. So we don't know X, we need to know X. So we will set up the equilibrium constant expression. So in this case, the stoichiometric coefficient is 1. So everything is going to be C raised power 1 multiplied by D raised power 1 divided by A raised power 1 and B raised power 1. Concentration, you see the square bracket indicates concentration. Okay? But if it has other values apart from 1, it's going to be raised to that power. Okay. So if we do that, then it's going to be for C and D at equilibrium, we said the concentration is X. So X times X gives you S squared, as you are seeing on the board. And for A and B, the concentration at equilibrium is 2 minus X multiplied by 3 minus X. So if you look at that equation, it's a non-linear equation. And you want to find X. So how do you find X? You are looking for the root of that equation. Now this is a very simple equation because the stoichiometric coefficient here is 1, right? So if we have values for A, B, C, and D that is not 1, you will discover that the degree of non-linearity will be higher than that. And it might be cumbersome to solve manually. So it's the same knowledge that we use to solve this seemingly simple equation that we use to handle situations where the stoichiometric coefficient is not 1 and the degree of non-linearity is higher than this. Okay, so now that you have used your chemical engineering knowledge to set up the necessary equation, so what we are now doing, which is supposed to be the focus of this class, is to use MATLAB to now solve this non-linear equation. But I had to give you that background, that chemical engineering background, so you could follow through. So how do we solve this? So I propose that we should first of all list what we are given. So what are the things we are given? We are given initial concentration of it. So let's call that A0, right? So we say A0 is what? Is 2. Okay. What else are we given? We are given B0. So we call that, what's the value? What else are we given? We are given C0 to be what? 0. What else are we giving? And what's the value? Okay. What else are we giving? Equilibrium constant. Okay. What is the value? 10. Okay. Have you captured all of the given data? So I believe we have captured it. So what do we do next? What do we propose that we should do next? So we are going to find x so that we can know what is 2 minus x, which is the concentration of A at equilibrium. So we could determine what is the concentration of B at equilibrium, 3 minus x, and the concentration of C and D. So we are going to determine x. So what do you propose that we do? So we are finding the roots of the equation. We have the equation K equilibrium equals to x squared divided by 2 minus x multiplied by 3 minus x. We are going to find that root. Once we get x, which is the root of that equation, then we can solve for 2 minus x, 3 minus x, x, and x. So what do you propose that we should do? Yeah, it will depend on the approach that we want to use. So let's say, for example, we want to use the function f0. So you want to use the function f0. I think I will propose that you will define the function such that the function equals to 0. So let's define the function. Let's call the function f. So we can say f is a function of x, right? So if we want to make that equilibrium equation equals to 0, what will it look like? That equation K equilibrium is equal to x squared divided by 2x, 2 minus x into 3 minus x. We want to make it equals to 0. You bring one side to the other side. So I'm bringing what is on the right hand side to the left hand side. Another might choose to bring what is on the left hand side to the right hand side. We will still get to the same place. So that's our equation. So we can say K equilibrium right minus what? X raised to power 2 over 2 minus x multiplied by 3 minus x. I hope you get that. Okay, so that's our function. So now that we have this function, somebody might want to use the second method. Somebody might want to use the Newton's method. Somebody may want to use f0. Somebody might want to use roots function. But since the first two that I mentioned, the second and the Newton method, they are iterative, I don't think we want to go that route at this time, even though if time permits, we can compare what it is with the method I'm going to use. But f0, I think, comes handy here with the form of the equation that we have, because we already have the function, and what we just need is a guess, and it's going to return to us only one root. If we had used roots function, roots, we'll be having two values, and what we need here is just a single value. So that means f0 here is a good option for us to use, but we need an initial guess. So somebody was asking me the other time that, okay, how do we know how to guess, particularly in an exam? And I told you that for exam cases, we will give you what you need. But in this kind of instance, you can have a calculative guess that works for you. So we started, the highest concentration we had was 3 mole. Although the unit of concentration is mole per volume, but let's say 3 mole because the volume is going to be uniform for the system. We started with 3 moles. So the one that has 3 moles will be reducing. And the least value we had was 0. It cannot be lesser than 0. And that 0 will be increasing. And based on stoichiometry, it's not likely that the one that is increasing will increase more than 3. Based on the relationship, the stoichiometric coefficient relationship. So we know what the highest value was. We know what the least value was. And we know what we expect, that there is no situation where we expect that the value of the concentration after equilibrium should be more than 3. So you know that what you are going to guess should be somewhere between 0 and 3. Okay? So that can help you in your guesses sometimes, so you can make a knowledgeable guess. So for this problem that I said we should use F0, so I'll be guessing 0.5. Okay? So you can guess any other value, at least up to 2.8. If you guess up to 2.8, I believe you still get the same value that I will get here. I can elaborate on that later. So I'm using 0.5 for my initial guess. So I can say that the root to that problem, which is x equilibrium, or simply x, is equal to F0 yeah, if you had used x equilibrium, x underscore equilibrium in the equation, then we could have used x equilibrium. But since we tie the function to x, so we will use x for it to work. So we pass in the function followed by your guess. So our guess here is 0.5. Okay? So now that we have that, then we should be able to find what the concentration is at equilibrium. So at equilibrium, what is our concentration? Based on the material balance we set up. X equals to F0 is going to give us the value of X. So for each of the species, what is the concentration at equilibrium? For A, the concentration is, so let me call this A. The concentration is going to be 2 minus x, but instead of using 2, we have said A0. So let us call A0. A0, which is the initial concentration, minus x, right? So what's B? B is going to be what? B0 minus x. And what's going to be the concentration of C at equilibrium? It's going to be C0 Okay, let's just call it x, or we can say C0 plus x. C0 plus x. Sorry, that x is supposed to be small letter all through. That C0 plus x is going to work in a situation that when you are starting, you already had some product. But in this case, the initial product is 0, so it might not make much difference. But for the case that, okay, we already had something when we start, then you can factor that in. Okay, so we have this. So when we run it, we expect that we should have our result, because what will help us find our result is the root, finding the root of that equilibrium expression. So let's try and print what the result is on the screen. So let's say the equilibrium concentrations of A So let me put a placeholder. So the same order that I mentioned the variables, that's the same order that I will pass in the variables. So I have A, B, C, D. A, B, C, D. So let me move to the next line after printing. So we can run it and see what the solution is. So it has printed the answer for me. I'm using live script, so that's why it's here. So it says the equilibrium concentration of A is 0.2466, B is 1.2466, C is 1.753, and D is 1.753. So that's it. Okay. Any question based on what we have done? You have to copy it. You have your notes, and the idea is not to copy people's code, is to be able to develop your own based on understanding. I can write it another way another time. Okay. So the major thing is that you understand what I'm doing. So the first part of it, let me explain what it does again. You see that it's in quotation, so that means I'm talking about string. So I want something typed, which is string. So what I want to see is the equilibrium concentration of A is a particular value. So that particular value is a variable that I've created. So I can't put that variable inside that string. So I created a placeholder for it. So I know the value is going to be a floating number. So that's why I've used F. Then I want 4 decimal places. So that's why I said %.4F. That 4 is talking about 0.4 is talking about 4 decimal places. Then I want to see also in that text that is going to print out, concentration of B is a value. Okay, so when I'm done saying what I wanted to see, then I will now pass those variables that I created placeholders for in the same order which I created the placeholder. How do I do that? I put a comma after the strings I'm looking at, then supply the variables, and that's it. So don't memorize my code, it will get you into trouble. Okay, I've said it before and I said it today, is to move the cursor to the next line, the command prompt in this case to the next line, so that it looks more presentable. Any other question? So we have applied root finding technique to a chemical engineering problem. And what we have used today is F0 for this particular problem, because we feel that it's best suited for it. But since we have more time, let's explore finding this root using other technique. Okay, so let's start with using the roots function. If you want to use the roots function, we said we are going to create a vector which is the coefficient of all of the powers that is available in that equation, right? That was what we said in the last class. So that means this equation that we have is not going to fly the way it is, because first of all, the equation must look like a must look like a polynomial. And in this case, since the highest power is 2, it has to look like a quadratic equation. So the equation we have was k is equal to x squared divided by 2 minus x multiplied by 3 minus x. So let's go back to what Alero said the other time, that we should try and rewrite the equation. So using that approach, we work for this root function that we are trying to look at. So what we need to do is ensure that that equation is looking like a quadratic equation that is supposed to be. So what do we need to do? An approach is that you might want to multiply k equilibrium, which was on the left hand side, by the denominator we have here. So we can have k into 2 minus x into 3 minus x will now equals to what? X squared, right? So you can write it down. So when it's equal to x squared, then we want to make that equation to be equals to 0. So what you can do is to expand that left hand side. So you multiply k through that 2 minus x and 3 minus x. So if you do that, what is it going to look like? Then afterward, you bring the s squared to the other side. So what's the equation going to look like for you? Work it out and let me know. Because we need to get what the equation looks like before we can move on. I'm waiting for your response. Okay, anyone with the answer? You know, that's what I asked you to do. You have the equation k equilibrium is equal to x squared divided by 2 minus x multiplied by 3 minus x. So I said make it look like a single equation. So get rid of that denominator and let us have a uniform equation. So that's what I asked you to do. Alero, any answers for us? Are we subtracting? Any approach is fine. So that equation will look like a quadratic equation after you are done. Let's go back to that equation to help you know what to do. So this is the equation. We want to use root function, and if we want to use root function, we will need the coefficient of all of the powers inside it. So this equation should look like a polynomial equation. So that's what you are doing. So that equation that we have on the screen is the same thing as saying Q equilibrium divided by 1 is equal to x squared divided by 2 minus x multiplied by 3 minus x. I think they must have told you somewhere along the line that you can cross multiply so that the equation on the right hand side can equal to equation on the left hand side if you want to get rid of the denominators, right? Okay. So once you do that, you have one equation here, the denominator has gone. Then you have to equate it to 0 for you to find the roots. So the right hand side can meet the left hand side, the left hand side can meet the right hand side. Just make sure that the equation equals to 0. Okay, when you need to expand, you will expand. For example, that 2 minus x into 3 minus x, you will need to expand. By the time you expand, when you move one from one side to the other side, you will see some common factors. You take the common factor, Then with that, you have something that looks like a polynomial. In this case, it should be quadratic based on the order that we have here. Then from there, you can get the coefficient of the powers that is inside your equation. So what's your equation looking like, please? Could you speak louder? X squared plus 6 k squared. We can't have k squared. Is anybody trying again? This thing is not hard. I have told you, imagine that k equilibrium as k equilibrium over 1. Cross multiply, that will give you 1 times x squared on one side. And the other side we have k multiplied by 2 minus x inside the bracket, multiplied by 3 minus x. So what we are expanding there is your 2 minus x multiplied by 3 minus x. That's what you are expanding. What? I mentioned that, but that is the part we are expanding, and everything we multiply through by k. So if we multiply through by k, k cannot get square. K cannot be k square. K will still remain k. That is what I'm saying. That's why I said the part we are expanding is 2 minus x multiplied by 3 minus x. So there is nowhere k is going to have square. Minus 5x here plus x on this side, right? Okay. And you might choose to use k to multiply through, okay, so that by the time you bring the x squared on the other side to that side, you can factor something. So anybody with the value? K inverse. How? Where is 1 over k coming from? You just gave me the expression, maybe the expression that should be on your left hand side, and there was x squared on the other side. So if you bring it to this side, I never said that. You will determine your solution. Okay, Alero says what? K minus 1 x squared minus 5k. It's not minus 5k, it should be minus 5kx plus 6k. Another person might have something, the sign might change through for another person depending on how you moved it. So some person might have 1 minus k into x squared plus 5kx minus 6k. Another person might have that. Okay, So I think we can, now that we have that, let me quickly show you an example for using the roots equation. So this is the equation that we should have. Okay. So for you to be able to use roots, you need the coefficients of the powers there. You need the coefficient of the powers there. So just using k will not work this time around. So you have to put values of the value of k, which is 10. So that equation will now metamorphose to 9x squared minus 50x plus 60. So that's the equation to solve using roots. Okay. So let's turn this to a function. So we can say this time around our f equals to right? So then we look for the coefficients of the powers in our equation. So what are the coefficients for this question? What are the coefficients? We have 9, we have what? Minus 50 and 60. Alero, right? Okay. So what's the next thing? We say roots. Is equal to root of p. So let's print the roots. Or let's just display it. So let's see what the value looks like to us. Okay, so using that approach, roots, it has given us the roots. So the root is what? 3.8022, 1.7534. Using that 1.7534 was one of the values we got initially for x. So this is the second root. So this brings you to your engineering knowledge. You know what is right and what is to be discarded. Now this is roots. You have two values of roots. Based on the explanation I gave to you, the stoichiometry, you have looked at the stoichiometry. There is no way any of the species is going to have more than 3 at the end of the reaction when it attains equilibrium, right? So you know that that other value does not make sense. So everything is going to fall between 0 and 3 at the end of the day. Okay? So that was one of the reasons I picked the other method, so that I can have one root, and I picked the guess value so that it's going to give me the value that is close to what is reasonable. So if I am choosing something like 2.9, it's going to converge to the other root, which is 3.8 something, and it's going to compute other things based on that, which is not what I want. So when you want to choose a guess value, if you know that you are going to get more than one root, you pick a guess value that will make it converge to the solution you are looking at. So if I had picked 2.9 9 is closer to 3. 3 point something, so it's going to convert to that, which is not what I want. I hope you get what I'm trying to say. So you pick your guess value so that it can converge to the nearest solution. And that nearest solution should be the solution you are looking to get, not the one you don't want to get, not the one that is not valid to you. Any question? If I had used the iterative method too, if I have picked any random value, that value is going to convert to the solution that is closest to it. So I have to be objective in choosing my initial guess. Then iterative computation will not be suitable for this problem because I need to be iterating until I get my solution before I now use it to solve for my equilibrium concentration. So that's why F0 is better here, more so that it has incorporated other techniques to have an effective solution. But you can try to find the root of this solution using other iterative method. You will still have these two solutions that is on the board. Any question on what we have done today? Okay, so that's it for this class.